do anything. You all see my screen in presentation mode, I hope.
Yes, we do.
Yes, we see it.
Perfect. So I think it's 3 o'clock and I think it's time to get started. Welcome everyone to this webinar, Motion Capture in Engineering. It's my pleasure to host it. I'm Louise Mattsson from ProPhysics SOL in Sweden. Let's start with some practical points. This is the agenda for the meeting. I will start by doing a short introduction to the MoCap Alliance. And following that, we have 3 presentations. Each presentation will be 20 minutes. And after that, there will be 5 minutes for questions and answers. And we ask everyone to put your questions in the Q&A part of Teams, and then Nicole will help us afterwards to sort those questions. After the 3 presentations, there will be a short presentation by Florian from ProPhysics AG on humanoid tracking, and then there will be some final words for today, at least. So short on the MoCap Alliance, the Alliance was established in 2023, and it's a collaboration of 4 Vicon distributors. It's ProCare, who are responsible for the Benelux area, so Belgium, Netherlands, and Luxembourg. It is ProPhysics AG, who are responsible for DACH, which means Germany, Austria, and Switzerland. GPEM are responsible for Italy. And ProPhysics SOL are responsible for the Nordics, which is Finland, Sweden, Norway, Denmark, and Iceland. And together we cover all the motion capture markets, which is typically life sciences, it's virtual effects, and it's engineering, which is the topic today. These companies have been around for a lot of years. We have a lot of experiences. And we thought that it would make sense to join forces because we sell the same products, we face the same challenges, and we have the same type of customers. And we feel that the sum is greater than the whole, and together we are stronger. We realized that we could share a lot of resources. We all do some development that we could share, and we all create bespoke solutions for our customers. So it made sense to collaborate. And we have been trying to find out ways that our customers could also somehow tap into this collaboration. And these webinars are an example of this. And this is our 2nd webinar, and we hope there will be more in the future. So that brings me to the first presentation of the day. The first presenter is Dr. Sihao Sun from Department of Cognitive Robotics, Delft University of Technology in the Netherlands, whose research focus is planning, estimation, and control of aerial robotic systems. The title of the presentation is Collaborative Aerial Manipulation, Multi-Robot Cooperation in Action. Dr. Sihao Sun, the floor is yours.
Okay, thank you very much. Thank you for the introduction, and also thank you for inviting me here. It's my great pleasure to present our recent work here. And just bear me to share my screen. I guess you can see that. Oh. Yeah. Okay, so hello everyone, and my name is Sihao, and I'm currently a Vini researcher from TU Delft, and I'm currently embedded in the Department of Cognitive Robotics. So the title of my presentation is called Cable Suspended Aerial Multi-Lifting System, So the name is rather complicated, but from the picture on the left-hand side, you can tell that what I'm describing is that we want to use multiple drones, quadcopters, to carry and also manipulate the orientation of this cable suspended payload. So why do we do that? As we know that actually for the cable suspended payload carried by the aerial platform has been a long-standing approach, and we have seen that in many domains already, in particular using helicopters. So for instance, we see helicopters for the logging and for like transportation in the construction materials and even in some military purposes. But also in recent years, and we also saw some development of the heavy lifting drones, and there's some deployment of them in this offshore transportation scenario. In particular, the one on the top right, what you see here, is the heavy lifting drone developed by an Italian company. It's called Flying Basket. So their drone can lift up to 100 kilograms. And now they are collaborating with the companies in North Sea to carry the equipment to the offshore wind turbine. So actually, there are many applications possible, not only in Europe but also like the global wise. But if you look at these two types of loading methods in the general landscape of the aerial carrying, and you can see that actually there are still a big gaps between the current technology and our like requirements. Okay, so on the very left-hand side, and that's using the small UAV for carrying the payload. And apparently, the problem of using a relatively small UAV to carry that is the payload capacity is very limited. So for now, the biggest quadcopters or octocopters that can which can carry payloads, it's around roughly at a range of 200 kilograms of payload capacity. And since most of them are battery powered, so they also have a very limited endurance. And if you look at the helicopters, and of course they have a much heavier payload capacity, but the problem is that they will require very high cost for operation and also relatively high pollution. So if we want to fill the gap in between these two categories, and either we make the helicopter smaller size or we enlarge the size of the UAVs, but they won't fundamentally solve the problems of these two categories. And another solution is what we proposed here, and you may also already saw some recent videos released by the DJI 2 days ago. So basically, we can use a team of UAVs to collaborate and carry this payload, because we can change the size of the UAVs and the numbers of the UAVs included in the team. So basically, the payload capacity can be much largely increased, and without the need to develop very large scale UAVs. And this will basically have the advantage of the both categories on the left and the right hand side. And even on top of that, if we think about the future, potentially we can also make the helicopters unmanned and make them fully autonomous. And then we can also use our algorithms to team up many heavy lifting helicopters. And then we can even lift the payload that's much heavier, and even like over 100 tons, for instance. And this is a science fiction movie from the Pacific Rim, and some of you may already saw that. I know it's a bit of exaggerate, but potentially in the future we can also achieve something similarly, right? Like carrying a huge material like a bridge or like the wind turbine blade to the offshore scenario. So that might be possible. Okay, now we're back to our life. So to develop and test these algorithms, and in our lab, we can't make a very big platform because it's mainly for prototyping. So the platform we're using is actually a very lightweighted UAV, and here that you can see it's a self-made UAV, and the takeoff weight it's only 650 grams. and we use a Raspberry Pi 5 as the compute module on board to run our algorithms or partially run our algorithm. And you can see that since we do everything in the indoor environment, and we also attach the OptiTrack or the Vicon markers in order for the motion capture systems to provide the pulse measurements. And of course, if we want to move forward to the outdoor environments, we're gonna change this one to like the RTK GPS or together with the magnetometer. So those together with some other sensor fusion algorithms, but those will be the future work. So then with our platform, so what we have achieved, as you can see in this video, is that we can use 3 or 4 UAVs to collaboratively carry payloads. On top of that, we can also change the orientation of it. And here you see that we can even change the shape or the configuration of this team of robots in order to really squeeze into this horizontally oriented gap, which is even narrower than the head of the entire system. And this is another example. So we put a vertically oriented gap, which is also narrower than the size of the entire system. And you can see that our algorithms, they can generate these receding horizon trajectories and send them to the 3 UAVs included in this task. And you can see that when 3 UAVs are following these trajectories, they can avoid these no-fly zones, but on top of that, they can also control the payload and even change the inclination of the payload in order to really squeeze into this narrow gap. So by providing a global trajectories, our system can follow that. And here you see that my colleague also throw a basketball into this basket-shaped the payload to induce some additional, let's say, like sloshing disturbances, okay? And these disturbances are also not being considered by our algorithm beforehand, and basically our method can react to this sudden change of the payload, so to show its robustness. And here's an overview about our algorithms. So first of all, I want to mention that it's a centralized solution, so it's not decentralized yet. So you can see on the left-hand side, it's the centralized part, which is being executed off-board. So it's on my local PC. And on the right-hand side, those are the quadcopters, okay? You can have multiple quadcopters and they run their own flight algorithms on board. So if we look at left-hand side, so the centralized part includes a online kinodynamic motion planner. So basically it can generate the receding horizon reference trajectories for each quadcopter using the quadrotus model together with the load and the cable model. So since we have the model of the systems and we also know the limitation of the system, then we can ensure that the trajectories we generated by the planner can also satisfy the constraints of the quadcopters. For instance, we want to ensure that the trajectories is not too aggressive so that it will overload the quadrotor, or we can also ensure that the trajectories can avoid the obstacles, just as we have seen in the last video. So here on the bottom side is an estimator. So the estimator provides the necessary states of the payload, and it's being fed into this motion planner on the top. The input of the estimator is the position of the quadrotors, the velocity of the quadrotors, and their IMU informations. Then you can see that it has a very strong advantage is that we don't have to attach any additional sensors on the payload. So by only using the informations from the quadrotors, which is already there, we can generate a relatively reliable estimate of the payload states. And this can be very, very practical because in practice, you can't always attach sensors or IMUs on the payload that you're carrying, right? So this is another example that we explored recently. So here you can see that I use 4 of those small UAVs to carry a very large scale space frame. So the space frame weighs 3 kilograms. It's still quite lightweighted because it's made from the DIY font of my daughter. And the size is 3 meters, but you can still see that we can already change its orientation in a relatively faster speed okay, without violating the constraints of the drones. And this can already imply some potential future applications. For instance, this is one fundings that we recently got. It's about how to explore using these solutions for construction. Okay, if we can use multiple of these cable suspended aerial motor lifting systems, or call them CAMOs, we can really deliver the prefabricated building components on site, change its orientations to put it at the right location. And we could also use our other like aerial robotic manipulators to help with these assembly procedures. I think that could open up a lot of like opportunities, okay, in the future. All right, so until now, the methods that I developed, it's centralized, right? Then from the academic point of view, a very interesting question is that, okay, how can we coordinate multiple UAVs without a centralized planner? Because if we use a centralized planner, it means that, first of all, we will rely on very reliable communication data links, because you need all the UAVs to communicate with the centralized planner very reliably. And another caveat of the centralized planner is that the more agents, the more UAVs involved into the planner, then the heavier computational load it will require, and that will limit the potential of this approach. Because imagine if you want to involve over 10 UAVs or even up to 100 UAVs into this problem, then it won't be possible with the current centralized planner. So then we need to jump into some exploration about decentralized solutions. So the first idea naturally come to our mind is to try with some imitation learning approaches. This is a diagram about a recent work from our team. You can see that here we still have a teacher policy, which is the centralized planner that's showed in the previous slides. And here's the environment. And you see that we have like the student policy in the form of physical informed neural networks. And then we can train these neural networks by imitating the behavior of the teacher policy. And since they already have imitated behavior of the teacher policy by using the output of the teacher policy in the training environments, then actually those single neural networks, they can also be executed with only the local observations of each agent. So basically, they don't need to observe the states of the other agents. They only need to observe the states of themselves. And then we don't have to limit the size of the pins or the numbers of pins. And we can also deploy each pins on each quadcopter. And this will allow the quadcopter to operate without a centralized planner, because during the test time, the teacher policy is completely removed. So here's an architecture of the teacher policy. I won't dive much into the details, but you see on the left-hand side, we have an encoder, which requires the states of the payloads and also the states of the drones by themselves, as well as the reference trajectories. And then the encoder will encode these measurements into the latent embedding space. And then we will have a decoder on the right-hand side to generate the reference trajectories for each quadcopter by themselves. And since the decoder also takes into account the physical constraints, so basically the velocity, acceleration, they should match the first order and second order derivative of the position outputs of the neural network. And then we can also ensure the smoothness of the reference trajectories that each quadcopter is following. And this is very important for the smooth execution of the task. And here's a demonstration about the generalizability. You see that this method can also be generalized to the data set, which haven't been seen before, because on the left-hand side, this is the training set. You see we only train on the circular trajectories, on square trajectories, and lemniscate trajectories, of course, with different velocities and accelerations. And in the test time, we validated on a trajectories which is never seen in the training set. But I think it's possible, because if you only look at the subset of like each portion of this validated trajectory, actually, you can already see that it's within the distribution of the training set. But it's just about how to combine these data sets into this unseen validated trajectory. So the problem of this first decentralized solution approach is that you can tell that we still need a centralized teacher policy. So basically the performance of the imitation learning based student policy is upper limited by the performance of the teacher policy. So that's the main issue. So therefore, we also tried another approach. It's the multi-agent reinforcement learning. So it's a completely different paradigm of finding a student policy. So in this case, there's no centralized policy at all, but instead we build a simulation environment in SXSim, and then we train the multi-agent reinforcement learning. Then we can train the RL policy in a centralized training and decentralized execution framework, because here we have a centralized critics, which has the global state, then it can generate the value functions based on the global observation, because it knows everything. But for the actors that we trained, it only have the local observation of each agent. So basically, each agent only knows their own state. They also know the states of the payloads. And then the action space was selected as not the RPM of the drone by themselves, but the actions is the acceleration and the body rate of each quadcopters. And then during the deployments in the real systems, we also need to use the onboard flight controllers in order to shrink the gap between the simulation and the reality. And you can see that with this low-level controller deployed, we can also deploy our algorithms in a real-world system in a single shot. So the benefit of this reinforcement learning approach is not only achieving a similar performance of the teacher policy, because we also see some behavior that can emerge from this multi-agent RL. So here's an example. You see that we have 3 drones hovering, and all of a sudden we switch off one of the UAV, and you can see that the remaining 2 UAV can still maintain, well, first of all, they won't crash, right? And on top of that, it can even change the remaining degrees of freedoms of the payload. Like we can change the heading by 180 degrees, and we can even change the position of the payload after the failure of the single UAV. But this scenarios is never seen during the training environments, but it does emerge in the real world scenario. I think that this is something very, very inspiring, because it can also demonstrate that, okay, our solutions can also be relatively robust and also safe in the real world scenario. Okay, the last piece, I just want to share some future and ongoing works, and so you can tell that to deploy the system really on the real world scenario, it's still a long road to go. So we are working on the wind resilient control. So if there's like heavy wind blowing on the payload or on drones, how can we maintain the stability and also ensure the positions of the tracking? That's one major challenge. The second challenge is to deploy the system in outdoor environments. Then we need to resolve the state estimation in outdoor. We will need to develop the sensor fusion between, for example, cameras, GPS, and multiple other sensors. Last but not least, some algorithms are still deployed off-board, like the centralized part, and how to make sure that we can deploy everything on board is also an ongoing challenge. Yeah. So that's everything I want to share. And thank you very much. Open up to questions. Yeah.
Thank you very much. We have a few minutes left for questions, if there are any. Nicole, have we got any questions yet?
We don't have any questions in the Q&A, but people have time.
You sort of touched on the very question I had in mind when I listened in the end. Oh, I think we have a question there from...
I think we have a question too.
Yes.
Can you unmute yourself, Sally?
I don't know if there was a question there from you, Saleh. If not, my question was basically, are you in somehow, when you go to the decentralized or the solution where you have all the drones moving in a team, are you still in contact with them, or it's not possible to then control anything anymore if a drone goes rogue? Are you able to do anything?
That's a good question. Yeah, because in the experiment environments, of course, we still have control for that. Like, of course, there will be some like a high level safety guard to ensure that they won't go crazy. And if they go crazy, we can also have a centralized approach to take over them. That's for sure. But I believe in the future, in the real world applications, it's really depending on the autonomous level, the level of autonomy that we want it to go, right? Like if you look at the current humanoid robots and the deploying in factory environments, and we want them to be fully autonomous, but of course there must be a safety guard to ensure that they're still under control by us. Yeah. So I think the same principle should also apply to our system. Yeah.
Thank you very much. I think we have to move on to the next presentation, or we will take minutes.
We have one question. Can we do that?
Go ahead.
You see, Mira?
Hello, can you hear me?
Yep.
Yes.
Shin, thank you very much for your presentation. I just have a quick question. Have you measured the latency when you try to stream the data to the drones?
Yeah, the latency. Yeah, it's we didn't measure that with very so we don't have a very nice quantitative results because we are still using Wi-Fi in the lab environments. So I can't give you a very clear answer for that. But my yeah, I guess it's at the level of 100 milliseconds and roughly like that, because we also simulated these latencies in our simulation, and we know the upper bound of this latency can be like half seconds. If we have a latency that is about half seconds, then of course there will be a problem for the decentralized solution. But if less than that, it's typically fine, because half seconds may sound a bit long, but I think the reason is because what we send to the drone is not a single command, but a trajectory. So even though there's a latency, and the drone still knows what trajectory to follow before the next trajectory arrives. So that's helpful with guaranteeing the stability. But regarding the latency in the lab, I believe it's less than half second. Yeah, that's for sure. Yeah.
Thank you very much. I think we have to proceed now to the next presentation. Thank you very much.
Okay. Thank you. Thank you.
Here we go. This. So the next presentation is by Professor Marco Sabatini from School of Aerospace Engineering at Sapienza University of Rome, whose research focus, I believe, is the modeling of dynamics and the design and implementation of navigation and control subsystems for complex space systems. And the title of the presentation is Laboratory Tests for Autonomous Space System. So, Professor Sabatini, please take over.
Yeah. First of all, thanks, Luis. Can you hear me? Yes.
Yes, we hear you.
And also, of course, thank everybody for joining this webinar. My name is Marco Sabatini. I would like to show in this short presentation some of the laboratory activities that we do at the School of Aerospace Engineering at La Sapienza in Rome. concerning different aspects of the orbital activities. In particular, I will focus on two aspects. So the test of attitude control systems, so whatever is needed to measure the orientation, control the orientation of a spacecraft, and also proximity operations. So all that kind of missions in which more than one platform is involved, for example, for in-orbit servicing, debris removal, activities of this kind. But the question is, how do we test this navigation and control system if we don't have a space station? Because of course the main road, the easiest one, would be to build a mock-up of the satellites and then test in a microgravity environment, just like in a space station. If you have a space station, then you can also hire maybe an astronaut performing the experiment for you. Now, I asked my administration if we could buy a space station. They didn't say no. They said maybe you'd better look for some alternatives. So what is usually done in terrestrial laboratories is trying to replicate some of the aspects of the orbital dynamics. The main aspect, of course, is the fact that you don't have a strong gravity in space. On ground, you cannot remove gravity, but you could try to remove some of the effects of gravity. In particular, you would like to remove the reactions between the subsystem under test and the table, the support. So basically, you should remove the friction. If you do so, you can try to simulate orbital dynamics, even if limited to some specific aspect. So, for example, if you want to test attitude control systems, you would go for spherical air bearings in such a way that you have a body that is able to move almost without the effects of gravity around the central body. If instead you have to test multiple platforms and you are also interested in linear motion, then you can go for planar air bearings. In both cases, what you need to do is to give up some of the degrees of freedom of the space systems. In both cases, you just simulate 3 degrees of freedom, so 3 rotations in the first case, 1 rotation and 2 translation in the second case. Another approach, completely different, is just to test the hardware in the loop by simulating the motion of the satellite, for example, with robotic arms. In particular, this happens if you want to test relative navigation subsystems and you are not really interested in testing the effects of the control of the satellite. So in my presentation, I would like to show all of the three ways of simulating the orbital dynamics. I will start with the attitude control systems. So we realized this facility in our laboratories. The goal of this facility is to test both navigation and control subsystems. So, for example, magnetometers, magnetotorquers, reaction wheels, sun sensors. So what we had to do is to recreate the orbital environment also from the magnetic point of view, from the illumination point of view. But of course, the core is the removal of the gravity torques. So So the black box that you can see here is the device under test that usually is a microsatellite of the CubeSat class. The main concept is that for removing the torques due to gravity, you should have the center of mass perfectly coinciding with the rotation center of the system. If it is above, you have basically an inverted pendulum, so you have an unstable motion and the platform will roll over. If it is below, it is stable, but then you have harmonic motion, so this is not what you have on orbit. So what you would like to have is a center of mass ideally coinciding with the center of rotation, but maybe with possibly a little bit lower, so that we are not sure that we don't go in the unstable region. To do so, we have to make a balance system. It could be an automatic balance system, it could be manual. We choose to go for the manual balancing because, of course, automatic system could ease this task, but could also increase the mass with motors, moving masses, and so on. So the main components, apart from the mass balances, are the Almos gauge, which must be able to replicate the time-varying magnetic field that is sensed by the satellites during its motion around the Earth, and the sun simulator, which must be able to simulate, of course, also the eclipse time and so on. One of the main aspects is the external metrology system, because of course we have to know the ground truth of the attitude of the device under test, and we used 4 Vicon cameras in a very compact setup, which was quite extreme because the view of the cameras was cluttered by the structure of the Almos gauge, but at the end we managed to achieve very good results that we show in a second. The device under test must not have any connection with the external world, because of course every connection would change the forces. So everything, every sensor, the Almos gauge, the sun simulator, the Vicon cameras are connected to a desktop PC, and all the information are exchanged via Wi-Fi with the device under test. We had to characterize this facility. So first of all, we wanted to be sure that the Vicon system was able to measure quite accurately the attitude, and we compared the a very tiny rotation. Basically, it was the difference between these two configuration was like a sheet of paper at one of the tip end of the facility. We had a precise bubble level, and we compare with the measurement from the Vicon system, and we had very good results that were more than in line with our expectations. And up to now, I have talked about frictionless motion. Of course, it is not really frictionless. It's micro friction, but there is some friction. So we had to estimate how much is this friction by measuring the decrease in angular velocity in a free rotation. And also we had to, for each experiment, measure the unbalancing. For us, the measure of the accuracy of the balancing procedure is the period of the free oscillations. If the period was about 20 seconds, for us it was satisfactory, because for the inertia and masses that are involved, it means that the misalignment of the center of mass that is sub-millimeter. So this is the level that we are happy with. And once we have characterized everything, we can simulate our space mission. We can simulate a certain orbit with a certain illumination, a certain magnetic field, and we can also simulate controlled attitude maneuver. So in this case, our device under test just contains some masses and a single axis reaction wheel that, of course, is able to perform a controlled maneuver about one single axis per time. So here we can see a reorientation about the vertical axis. The other two angles are not controlled, but the controlled one is very satisfactory. And also it can be performed a reorientation about the other two axes, which are more difficult, let's say, because in this case, the role of the residual gravity starts to be important. In this case, the reaction wheel was like a toy wheel, so we did not expect so much performance, but we demonstrated that this is possible. Now, let's go to the second topic, which is for some aspect completely different but there are some commonalities. So usually in space proximity operation, you have two main characters. One is the target that could be perfectly functional and waiting for you, but could also be tumbling or even a dead body, a debris. And the chaser with a robotic arm, which has the goal to grasp this target. We focused on some specific aspect of this mission, so in particular path planning and control, not on relative navigation, which is quite an important topic, but for these experiments we suppose that this problem is solved. So somebody is giving the real relative state, and in this case it's the Vicon system that is giving this information. So the problem is that the chaser should catch a certain point, which is this yellow ring of the target, of course, without colliding with the structure of the target itself. So to do so, we fixed some zones to be avoided, and the role of the path planning is to define trajectories with some intermediate waypoint and a final approach line, so that all the structure are avoided and the grasping point is reached. To do so, we cannot just move the robotic arm, we have to move all the spacecraft and the robotic arm. So it's a complex problem with 8 degrees of freedom. The trajectory planning is a bidirectional, rapidly exploring random tree. I will not go into the details, but it's a random search algorithm. The bidirectional version has two branches starting from the target and from the initial point. The result is this scattered trajectory. We can smooth, of course, this trajectory. The good thing is that this line that reach the desired point without colliding is very fast. So we can recompute this path with 0.1 second sampling time, so that even if the target is rotating or tumbling or moving, we can always update this trajectory and achieve our goal. So how was this realized in our laboratory? We used both the approaches that we have seen in the beginning. So the chaser actually is not a free-floating platform. The spacecraft is represented by this rail, a linear rail, so it's just 1 degree of freedom, on which the robotic arm is mounted. While the target is a free-floating platform which is able to move, can be controlled or can be freely moved on this flat granite table. And again, the external metrology system is the Vicon system. In this case, there are 8 cameras in more conventional setup, and also with these distances and configuration, the accuracy that we reach in terms of linear motion and attitude are very satisfying. And so I will end showing 2 different maneuvers. In this first maneuver, the target is waiting for the robotic arm, but is in such a way that the robotic arm has to do some collision avoidance maneuver before grasping. So it cannot directly go to the target point, otherwise there would be, of course, a collision. It reached the intermediate point and then perform the grasping. After this, of course, there is all the post-dynamic study that is still ongoing. Final experiment is with a tumbling target which moving in an unknown way. So the trajectory, the fact that the trajectory can be recomputed very fast allows for the successful accomplishment of the maneuver. Our final goal is to validate with this experiment our simulations. So when we obtain this kind of results, we are say quite happy, because qualitative the experiments really replicated the simulation with some additional noise that is expected due to hardware inaccuracy, navigation accuracy, and so on. But this is the what we would like to do. It's not just testing space hardware, is more validating the hardware and validating our software tools for the simulation. So I think I can stop here and leave the floor to the question, if there are some. Here there are my contacts, the email, and of course, thanks for listening. And I hope there are some comments or questions.
Thank you very much for a very interesting presentation. I hope we have some questions. I see there are no questions in the Q&A, but maybe there are some questions from the floor. So far, I can ask a short question. I know customers that are working in this type of field, that are, when you try to control these different degrees of motion and they try to simulate a space situation, and they use hyperbolic flights to simulate a situation with no gravity. Is this something you are doing in any of your studies? I understand the management didn't want to buy a space station.
Yeah, I think parabolic flights are not expensive as a space station, but not even for free. No, the main point is that parabolic flights just allows for very brief experiments, because
Yes.
the gravity-less part is of the order of tens of seconds, so 30 seconds and so on. So it could be it could be nice for some of the activities, but usually space activities, this kind of space operation takes minutes. So it is true that in this way you have real 6 degrees of freedom space-like scenario, but then you have to accelerate everything. So it's always a short blanket.
Yes, I understand. Right. I would like to say that for everyone who wants to send questions to the Q&A, please continue to do that. Our presenters can answer in the Q&A section directly to you. So don't hesitate to write your questions there if you want to ask them afterwards. So thank you very much again. I would like to introduce the next speaker. So our third presenter is Senior Research Engineer Elias Small from Department of Computer Science, Electrical and Space Engineering at Luleå University of Technology, which is here in Sweden, but still 1,500 kilometers north of where I am. So Elias will have to tell us if spring has come to Luleå yet. And the title of his presentation is Field Robotics and Robotics Autonomy Enabled through MoCap. So Elias, the floor is yours.
Thank you very much for the introduction. As you mentioned, I live quite far away. I think you are closer to Italy than I am to you, though we are in the same country. So quite far north, the snow is just melting. We started to get a bit of grass coming out. So let me just share my screen here. So I work in the robotics and AI group, the robotics team that we have here at Luleå University of Technology. And what we mainly work with, as you can probably see by the title, is the large field of field robotics. Basically, we work in robotics, but with the aim of taking as much of our experiments as possible into as real an environment as possible. So the end goal is not just the simulations, but we try to implement them into more real life scenarios. As you can see by the picture we have here, this is a underground cave system where we are deploying some of our own built drones. You can see there's quite a lot that goes into having autonomous drones in the sense. They are quite heavy and require their own PCs on board to do computing. But to get to that stage, of course, we need to use motion capture because there's a lot of components that go into this. So first, I'll just give an introduction to our group. We are about 60 people up here. And what is maybe a little bit uncommon with our group is that we have a lot of engineers working here and this is mainly because we need to build and produce experiments to quite a large degree physically, and therefore, in general, there's in Sweden at least it's quite common to have maybe one engineer per lab or per group, whereas we have 8 for our 4 labs. We have a lot of subjects since we are quite a lot of people. Aerorobotics, inspection, service robotics, space robotics, as we saw in the previous presentation, similar things. Biorobotics, we work with industry, farming, even construction, autonomous vehicles, and even underwater. And I would say that when it comes to the motion capture, I think the only subject that can't really use the motion capture for is the underwater, since it's quite difficult to bring the system underwater. We've been chosen by the Royal Swedish Academy of Engineer Sciences as being in the top 100 contributions for the past 5 years. The result hasn't come out yet for 2025, but we're hoping to be there as well. So field robotics. I've chosen this picture to kind of show how much goes into bringing a system into a harsh environment like a cave system. Here you can see many of you recognize Boston Dynamics Spot, the dog. Of course, this is the platform that we're using, but everything above that is what we built here. So you can see the LiDAR up top and a lot of 3D cameras. Of course, there's a PC unit that's computing everything, taking care of this, IMU, inertial measurement unit. And the same then, you can see on its back, it has a drone, which in itself has the same system on itself. And this is completely self-built, since these high computational drones isn't something that exists in the consumer market, let's say. So field robotics, this is our main goal. We have, of course, some other focuses. We're going to touch on space robotics as well. And in our case, we mostly deal with planar motion, which is for instance, the docking and the final slides we saw on the previous presentation. And we also deal with traversability. So what happens when we get to planets, for instance? How can we make the robots more autonomous in their navigation, since there's a very large delay and it's quite difficult to steer and drive a rover that's on Mars, for instance, with an 18-minute delay. So we have this 10th scale model of Curiosity that's on Mars right now. And finally, when it comes to having robots in real life, a big question on everyone's mind is how do we make this safe? So this is another of our focuses of how can we make the systems work and also be adaptable to the unpredictability of humans. Let's put it this way. In this case here, of course, we're not actually using a Vicon system with this guy walking. That's why he's wearing quite some protective gear. This is using its own autonomous system. But of course, to get there, we needed the motion tracking system. So I'm just going to go through our lab facilities, and then I'll be showing some experiments and tests that we've been doing. We have 4 labs. Our first lab we call it the Frost Lab. Mostly themed because of where we live, but we call it the Field Robotics Lab, and obscurely shorten that to Frost. In this lab, that's where everything starts. It gets built from scratch. We have workshops. We have 3D printers. A lot of facilities for students and researchers to work. After that, things often move to a lab we call Concept Lab. That's what you can see here in the picture. I'll get into it soon, where we are able to, it's a much larger lab, and we're able to build environments that are suited for our tests. Then we have the aptly named Space Lab. This is a laboratory where we do the planar movement and experimentation for satellite maneuvering. And then the final lab, the Subterranean Lab. We have a laboratory that is underground in a cave space. We have both a little office space and also a lot of area for testing in the cave environments. And the first 3 labs here, these are all equipped with the motion capture system. Only the Subterranean lab doesn't have this, but we are able to bring it to that place if we need to. So this is a picture of our Frost Lab. We have this is our oldest lab, built in 2017, I think. As you can see, it's a much older version of the Vicon cameras here. We have 18 of them, which could be seen as overkill for this little room. But we do a lot of testing. We have, of course, the safety nets, safety mattresses, and as you might be able to see from these pictures, a lot of holes in the roof. This comes from, of course, the tests that don't go so well, and often that's how it goes in the early stages of development. We are also able, as you might see, to move them. We have these mounted on easy to detach from this rail. So we've moved the system onto a tripod system, so we can easily take it with us if we want to do tests in a different environment. Then, of course, we have the Concept Lab. Here we have a much higher to the roof, so we're 7 meters clearance. And you can see in each corner, we have 2 of these Valkyrie cameras that are facing inwards. And we have this huge setup of basically building blocks. We create environments for our robots. Sometimes, of course, we don't use that, but we have large ability to adapt this room to our needs. And also rubber flooring for when things don't go as well as we intend. Then we have the space lab. The room is quite small, so I have a render here, since you can't see everything in the photograph. We have a compressed air station with our own generator, where each of these robots, we call them sliders. They are mounted on these 3 planar air bearings. So this surface is very similar to as we saw in the previous presentation, as frictionless as possible without actually having to go into a real frictionless environment. These are powered by compressed air, and each of these robots also has thrusters that is also using the compressed air to simulate the thrusters of satellites. So there's in each of the corners there's 2 thrusters pointing in 90 degrees from each other. So, and they also are in a on-off system rather than continuous to make the maneuvering as hard as possible, basically to test our control algorithms. And we also have a 6 degrees of freedom robotic arm at the top, so we can have, for instance, objects moving around or interacting with these bots if that's what the experiment requires. Also, it has a extender, so it can come all the way down to the bottom and has quite a large reach. Then we have the last lab, which is the sub-training lab. As you can see here, it's almost 300 meters from the entrance to the last cave. We have a lot of area. So it's a decommissioned, basically a military station that we use the cave system, the old cave system, to do tests. Of course, mainly for the mining industry, which is one of our biggest sponsors up here in the north. But as you can see, the environments are very close to what you would get in a real mine or a real cave. So I'd like to just talk a quick point about to get to this real environment. Basically, we have this flow that's quite logical. Is that to test all of these control algorithms and the mathematics of it, it's always good to condense or remove the variable aspects. And in this case, the positioning and maneuverability, of course, is what we are able to get to a sub-millimeter level when it comes to the initial labs and the motion capture system. Whereas, of course, all of that, this system is replaced then by LiDAR, cameras, IMUs, and its own computation once you get into a real environment. And eventually, we get to the point of, as you see in the last picture, this is actual tests being done 1,700 meters underground at the LKAB iron ore mines up in even further north than where I live in Kiruna. So then I'd like to get into showing you some of the things we do. Now, of course, one of the main things with when we are working with these things is how do we have several things in the same room without them actually colliding with each other. So there are many different methods. A classic method is this, what we see here is an artificial potential field. Try to avoid and don't get too close. But what happens when things are moving too fast? And this is basically showing you what happens when an object is moving closer. Instead of just having a potential field, how about we try to predict where the object is going to be? And even that can be a little bit slow. So if you have what we talked about earlier, centralized system, in this case, the system is predicting both where the ball is going and its continuous trajectory afterwards. And as you can see, the drone is able to react as soon as it detects any motion that might be coming towards it. And here we can see that can even include bouncing, where it's moving out of the way for the bounce of the ball. And I'll move on to the next slide. Now, this system of trying to predict where the other objects in the environment are can be extended to multiple drones. So basically, these bots are going to exchange information with each other. Here we can see through the system that each one is sending its own trajectory and the others are reacting. So right now, these are just being given new positions and try to follow the empty path. But you also see that the other ones, through shared trajectory, are responding to this thing. We can take this even further then by and I'll just explain what's going to happen here. Here we have 10 drones in the air, and the only thing that they are instructed to do is to move across the room to their new position. And they will be sharing each other's trajectories through and predicting their trajectories, and then remapping at about 20 hertz their positions so they do not collide. And you can see this, what may look quite chaotic, but there are no accidents happening. And it's because of this very high speed calculation. And this can be extended. What happens then if one of them sort of gets detached from the centralized system? Can the rest react? Well, if they are able to see its position and give a somewhat estimation of where it's moving, they are still able to react to the system. So here's some of the things we are able to do with our predictive algorithms. Here's another example of interaction between a ground vehicle and a UAV. If we have a movement, and here we have a certain, you'll see from this, we have a certain area where we are instructing the drone that it's not allowed to be. And its aim is to land on top of this moving vehicle. And it's creating this, so basically the mathematics is creating a cone of sort of a dangerous area, and it's adapting live to this movement and trying to reach its destination, but without crossing the boundaries. Again, something that we, of course, move to reality, but to test these small algorithms, we need to be able to know exactly where each of the positions are before moving further. Here's more of an anecdotal thing. We've also cooperated with a dance show. Also together, this was an example where we had the Vicon system moved to a stage area where we have markers on the dancer's hands and also, of course, on the drones. And he's doing a dance where he's controlling them through his gestures. It was more of a artsy collaboration, maybe not as much of a engineering like a result-driven thing, but still very appreciated by the humaniora department of the university. And in this case, we were still using the model predictive control to try to prevent them from crashing into each other as they were doing swap maneuvers and so on. I thought I'd show one little video of on the space side. We were doing the docking maneuvers we were talking about earlier of this two-dimensional planar space movement. And in this case, this drone is tethered. This experiment is from before we had built our lab. But as you can see the Vicon markers, and we're using this system to then further extend, similar to the landing of the previous drone on a platform. Here we're doing the docking, and the control systems are using the air thrusters to try to then get this device on a frictionless surface to dock properly into its station. Some improvements can be made, but this is it's very cool that we can do this in a lab in a university rather than having to have expensive equipment and going up into space, or as you say, into dives with very large airplanes. And then finally, I'd just like to show some of the things we do with humanoids, which is quite new. We have, since about a half a year back, we've had some humanoids. So here's some cooperation when it comes to basically this mission we're seeing here. They need to stay in a triangular formation, but there are obstacles all over the place. And this is in our concept lab, as you can see, where the fake Lego blocks. These are also marked with Vicon markers, so that the information being shared is this global map we see to the right, with the pink are the objects that are completely untraversable, and the blackened areas are more dangerous or areas that should be avoided. And they're also aware of each other's presence, so they're trying to remain in this triangular formation, but at the same time being adaptive to what's going on. In this case, we've even done the experiment by a person holding one of them back, and the rest wait for that bot, and then once they have a sort of triangle, they keep moving, doing their mission. And finally, yes.
Yes, are you getting towards the end, or?
This is the final slide.
Good.
Yeah, just a short video of, again, with the humanoid, and I'll just explain before we see it. We see the markers on his head. He also has the markers on his arm and hands and on this can. So we are basically, there's a student who's going to be moving the can around, and it needs to adapt to that position. So it's not a hard-coded position. Its goal is to grip the object. And the information is being fed as the position of its hand, the object, and its head. And through kinematics, we're able to work out the rest of the body and the pose, basically. So there's ongoing research about using these to detect and to manipulate objects. One of our future plans is to get a bodysuit with the Vicon markers, so we can actually train more realistic and more complex movements. But at the moment, we have these that we attach to and refer to each of its joints as a separate object. Yeah, so that was the final slide. If there's any questions, I apologize for taking a bit too long.
No problem. Thank you very much for showing some really interesting use cases. If anyone has any questions for Elias, please put them in the Q&A, and Elias will do his best to answer them. I will now give the word to Florian from ProPhysics for a final, just get this going here, for a final short presentation. And your end there, Elias, with the humanoid tracking was a perfect, I think, pass on to Florian, who will take it from here.
Thank you.
Are you with us, Florian?
He's there. He can't speak yet. He tries to open his microphone.
All right.
It should be possible.
So now it's possible to hear me?
Yeah.
Oh, finally. So I could not unmute. Thank you, Elias. Yeah, it's true. You just opened directly to my maybe 5-minute presentation. I was asked quickly to talk about humanoids and what we're doing. We are the same. We have the same set of products, the MoCap Alliance, more or less, and we are servicing the same markets. And the ProPhysics is now seeing more and more of the humanoid market. What you just showed us, Elias, is just starting. I will share my short presentation. So I hope you can see it now.
Yes.
The question is, how are we preparing, or what's happening in the humanoid market? And so to say, preparing for the humanoid wave. And you may have seen this in the news, I think just this weekend or last week. A robot in China has run the half marathon world record and has beaten the fastest human by 7 minutes and made the distance in 50.5 minutes. If you think about it, last year the fastest robot was 2 hours in the, and most of the robots did not make the distance. So something is going on, and the question is why humanoids and why now? And the answer is clear. The market is obviously growing a lot over the next 5 years, 4, 5, 6 years. There is a growth in humanoid robots of about 30%, 40% annually. And why is that? That's because humanoids, the humanoid shape, other than the other robots that Elias showed and the drones that Elias showed, are able to work in an environment that has been designed for humans. So they can probably replace skilled workers or work like humans should in hazardous environments, for example. And I think that's the path why human robots are actually interesting. And the limiting factor, oh, I switched off my screen. So the limiting factor is getting the movement into the robots, training the robots to do the movements. That's exactly what Elias showed in the last steps. It looked a little bit clumsy still, the robot grabbing the object, and that's where the robots have to learn a lot if they want to be skilled workers. And now real pilots are going on with large customers, and customers, BMW in Munich, Amazon, Mercedes, Neura Robotics. These are customers that we know, but there are more customers everywhere in the world that start working really with pilots and having robots doing some work that is effective. So where do we sit? The words that you have to mark is teleoperation and data farming. And that means data farming means humans show how they move, how they grab things, how they walk, of course, but walking is less interesting than grabbing and working and moving things. And that can best be learned from humans, because for humans, it's all natural environment, grabbing, moving things. And if you can think about humans, or that we capture the data, that could be with Vicon cameras. We do a lot with Xsense suits and with Manus gloves. If you capture hundreds of movements or thousands of movements, you have a very good data cloud for robots that should do that movement only once, but repeatedly correct. And where is ProPhysics and where are we now in this area? There is the OEM that produces the robots. The robots will be available. The hardware will be available soon. They are producing already, and it's not the problem to produce the hardware. For now, it has been, and I bet Elias knows, because if you want to purchase a robot right now, it takes a long time, a lead time to receive one. They are quite expensive, but the production is rolling. And there is the companies that can provide the training infrastructure. This is where we are. And then next step is the system integrator that trains on data for the use of the robot. You can think of not just walking and grabbing things, but very complex movements. And all the robots that should work in the field need very precise and special movements. And that's what they have to be trained on. These system integrators will also be large companies that have cloud area, a lot of cloud data to store and to work on before the robot is programmed with a human-like movement or efficient human-like movement. And then there is robots as a service. There will be a lot of new startups, companies that will provide robots if you want to purchase that service. It's like a taxi. You buy for the service, and they deliver the robot, and they deliver the service. You just pay for that. The robot comes trained already. That's for the end customer. So, and we are in that area. We can see that this is really like a rocket is launching quickly, because there is so many opportunities you can go to. Of course, you need not only the sensors, you need to capture the data, calibrate the data, do the retargeting. The robot has different joints, although it is human, has limbs to move. It could have wheels to drive or quad pads. That wouldn't bother us, but to work in the human environment, he needs to be agile like a human, more or less. And so what ProPhysics is providing here is the infrastructure and the use of the infrastructure. That's the use of the Vicon system, the use of the Ixen system, of the Manus gloves, how everything is connected, and how the software is used finally to transport human captured data into the system and start working with that data. That's more or less everything I wanted to let you know. If you're looking for something in that area, you have to find teleoperation, imitation learning, digital twins. You will see that there is more and more. We've seen job announcements, hiring, and then you can see which companies are already trying to purchase robots, train robots. If you want to see what's happening in your country, some companies are going to purchase a lot of the robots. It's going to be hard for researchers to get robots because they're very expensive. And if someone is paying more for that and purchasing larger numbers, they will receive them earlier. It's a very, very interesting field. And we feel that we can be part of that. The robots will be around us in the next 5 to 10 years in different environment and different applications, definitely. Some, and for Germany, we can see that they shall replace skilled workers. There are not enough skilled workers in the automotive building companies, in other companies that produce skilled workers in the elderly care, maybe, but maybe that's 10 years or 15 years in the future. We don't know, but it seems that there is a lot of space for human robots.
Well, yeah.
That was it.
Thank you very much. I think it looks like there is a lot more to talk about here in this. Maybe this could be a subject of a future webinar as well.
Yes, surely. We are learning every day, and still we have to learn where is our space, what can we provide, to what degree, where do we need to learn new skills, what do we need to offer in the future. We have to find out, and but it's a very fast developing, and there are startups coming up, and you see these startups are companies that want to train robots and sell the robots services to other companies, to the firefighters and to the police and to skilled workers that are missing because not available anymore. So everyone has good ideas and wants to be part of that business. There's something going on, definitely.
Thank you very much. I think we have to end now. We have crossed our lines by a few minutes here. So thank you for your insights. And with that, I will just show the final slide for today. It's time to say goodbye. I'm sorry that we used a few more minutes of your time than promised. We have a short survey that we would really appreciate if you answer. These webinars are still quite new for us. We would like to offer more of them, but it's very good to know for us what kind of topics you're looking for in the future and how you like the format and the duration. So please take a minute and fill out this survey. The recording we will send a link to the recording of this webinar as well. And of course, if you have any questions regarding any of the systems shown, or if you want to get in contact with any of the presenters, please do not hesitate to contact us or and let us know. So thank you very much, everyone. We really appreciated your time.
Thank you.
Thank you very much.
Thank you very
See you.
much. Bye bye.